Hey, yeah, I guess we can start now. Um, I'll just review what we discussed last week. So we looked at operator overloading. So for example, we have operators equal to, right? And depending on the input that we take, as the x could be an integer or it could be a double. Fine. Or it could be double. We'll have different body of the function being called. Okay. So so the here the class is templatized. Okay. And maybe we can talk about that also. Yeah. So here the class is templatized. And depending on the template that we can have two different uh, the members themselves of can be of different data types. And correspondingly, when we use different operators, the equal to operator, we can have different bodies. Okay. So that's sort of the idea behind this. Okay. We also looked at the uh, popular or the very commonly used vector class and accessing data by using the bracket operations. Okay. So essentially, this is also a sort of a operator overloading where the bracket operations themselves are overloaded and the return types look something like this. Okay. So depending on what the well, technically, I wouldn't say it's exactly operator overloading, but you can think of it like this is how the definition is for the square brackets. The pointer to the object A, so let's which will be something like A dot data. So let's call that as underscore A pointer. It will be some internal member variable. That plus I does the pointer arithmetic. Okay. And then yeah. And then plus I does the pointer arithmetic. It's like it shifts. Dereferencing that returns the actual output at that location. Okay. So this is how the operator overloading works. Okay. Next we saw is class templates. Okay. So maybe I should start with this. Anyway, so there is a function called max. Okay. And we templatize the class. So T is the template and the two member variables are A and B of data type T. Okay. Now there is this is the constructor. Okay. The max itself, which takes two member variables. And the way I'm setting it is when I use the keyword this with an arrow and A, I'm referring to the internal member variables, which are private members. Okay. So these two are the private members. Okay. And when I say equal to A for in the scope of this constructor, it here the right hand side refers to this A and B. Okay. So this sets A and B to the internal member variables A and B. Yeah, that's done. Then I define another function called max of data type T, capital T. That will be my templatized type name. And then I return uh, if A is greater than B, then I return A using the ternary operation, else I return B. The usefulness of this approach is while the comparisons will be done for the same data type, I don't have to explicitly define what the data type is. I can I can use the class template as a blueprint to do this. So I can actually create objects for double, integer, and so on and so forth. So using integer, I create an object m, pass one into, calling the function max on m returns the larger number of it. Okay. Similarly, one can similarly, one can also yeah. So right. Similarly, one can also um, make use of minimum. Like you can also define something called a minimum. Do it for double. Okay, and then write the class and then basically define the object and use that function. Okay, so that's one example of how to use templatized classes. All right. The another thing is, hi, is there a question? All right. So yeah, the other example we see is we can have not just a single template, but we can have multiple templates for our class. All right. So you can define a main class with two data types, T1 and T2. Okay. Then you can actually then internally set them using the constructor defined as such, where as before, the keyword this with the arrow operation and a refers to the internal member variable. Okay. And the right hand side a, because it's in the scope of this constructor, it refers to this a. All right. Similarly for b, it refers to this b. Okay. And you can define a main function which returns of data type T1. And again, using the ternary operation, you can define the operation. One has to be careful here while using different data types. The return type here is defined to be T1. So if T1 is less precise than T2, then you might run into issues. Okay. So yeah, again, one has to be just careful. Okay. All right. So then similarly, the max function, and then we saw some examples. Taking another templatized class, we have, let's say class A, template T. It has a member variable V, which is actually standard vector. Okay. And the template for the standard vector itself comes from the templatized classes A's template P. Okay. So there is a init function which will init it with taking some number n. So what we can do is define an object for class A with the template integer. So now my vector is also V, vector V. Okay. It will also be initialized to be at integer type. Okay. It's a standard vector, but it will be of integer type. Okay. And then I can call init 10 to uh, resize it to have 10 values. All right. So one can have those things also. Then we also looked at what extern C means. So it's essentially like, let's say you have included a header file, which is some extra, I'm calling that as some external header file, okay, with some .h. And let's say it has some C functions. To access and use those C functions, you have to include them within external C. Okay. So now this function can be accessed in your C++ file itself, and you can call them accordingly. Okay. So the header file includes the function definition, says that this function, let's say it's called underscore multiply, with maybe it will take some inputs, which I have not put, some arguments. Then such a function with the data type void exists inside this header file, but its actual body may be hidden to you, as in it might be compiled and stored in some object file or some shared library. So while compilation, you link that library so to get the actual body, but all in briefly, the important thing is that the header file includes it just says that such a function with some certain kind of return type and certain kind of input parameters or the arguments exists and you can call it. Okay, that's sort of the idea. Okay, that's why you make header files also and include them in your files in your program while linking to external libraries. Okay, the library provides the actual body of the function. And sometimes if it's open source, you have the actual source code for that. Else, if it's not open source, then you don't. Okay. All right. So another thing we saw is of example. So I guess I can start templates again. So function templates. Let's say you have a function called max, which takes integers, returns integer, takes doubles and returns doubles. Okay. So can do the same operation using ternary operator, right? And you have to repeat the body here. So to avoid such duplication and redundant code, you can this the hence templates were born. Okay. So another way you can do it using macros. So to avoid code duplication, then hash define a macro called max, takes inputs A and B and returns. And so this is the body of the macro. Okay. So essentially what happens is when a max of 1 and 2 is called, it just replaces this body. Okay. With the since the inputs were A and B here. So it will replace A and B with 1 and 2. And then this body gets compiled at or evaluated, okay, at compilation time. All right, because first the preprocessor directive is initiated, as in its work is done. Okay. Then the second step, the compilation actually starts. So during compilation time itself, this body gets compiled, as in evaluated also. Now the important thing here is this comparison is independent of what the data type is, as in you might run into compilation issues if you can't compare or do this greater than operation. Okay, if the parameters themselves don't match, so you'll have comparison errors. But here, as such, it avoids the duplication of writing max twice and thrice or whatever. Okay, but there's a much cleaner way, and main reason is because macros are can lead to a lot of issues and errors. Okay, so there's a much cleaner way called templates, and the way you define it is something like this. So maybe we saw this before, but again, anyway. So the template is defined as with type name T, capital T. Okay, and capital T basically means the here what we mean is the return type or the input type that we take and compare it, right? So the max function returns capital T type and takes input parameters A and B of the type T, capital T. The body is same, and again, in both the cases, you can have if-else statements also. It is equivalent to writing some the ternary operation. There is a difference in terms of performance if you see, because if and else actually essentially mean branching. So branches will sometimes it depends on what case what the program and optimization happens under the hood, but usually branching can lead to degradation in performance. So ternary operation, you can think of it like it avoids that step. Okay. So you can do the same thing here. Now the neat part here is, let's say you define a max function with A and B. Okay. Here, I could have also passed with angular brackets what the type is, but because we are inputting A and B here, okay, of defined data types and C and D also. So it infers the capital T data type for return and input. Okay. The very nice thing or the beauty of templates is once you define a function actually with some as in template, then only this blueprint of a function exists. As in, let's say max is never called, then is there a question? Oh, okay. Just a second. Oh, no, no. I'm just reviewing last classes thing. I'll continue today's class after this. Yes. All right. Yeah. So the beauty of templates is a template like this, a function with a template like this actually doesn't get compiled at all. Okay, it just gets ignored if it's never called. So let's say I comment these two lines, then 17 and 18, and okay, furthermore 20 and 21 also. Okay, let's say we comment all these lines. So if the max function is never called, this function template doesn't get compiled, as in it doesn't exist. Okay, there's no um, portion or anything which gets as in memory allocated. Functions also get memory allocated to them. Nothing like that happens. Once you actually call the max with some template parameter integer, let's say, only the integer templatized max exists in memory or gets compiled. Okay, there's a definition, there is a whole memory allocated to it, function pointers and everything. And then in the second line, when we call for the double, then a copy of it, okay, exists something like this, with an integer with a double. So template get on the fly created, okay, as you go. And I mean, it's basically the how you uh, make each function. So call for it a certain template, then only then that function gets created, and so on. You can have as many templatized functions as you want. Okay, all right. So that I guess more or less covers last week's summary. So right. So let's go ahead for today's thing. Uh, we'll look at some input out IOs as in input outputs from both perspective of the file and as in the C++ is a normal input and output stream that we are familiar with, and from file perspective. Okay. Okay, exception handling. Yeah, I guess I can do that also. Okay, let me cover this and then maybe we can also do exception handling. Yeah. All right. So input output, right. So as usual, we'll include the IO stream file, header file. The so the IO stream is what we use, right? To get STDC outs, STD, ENDL, and so on and so forth. So let's take the basic example, and then we'll go in deeper details. We'll write the main function. Let's say there is an integer a, which is 6.7. Sorry, it's an integer. A double b, which is 7.1, and let's say there is an integer c. That's it. Not set to be anything. We can have c in, right, to c. So here it means whatever we enter to inside, like give to the terminal while we run this program, the input to the from the terminal will be set to C. That's what standard C in is. It's the input stream, okay? And notice the angular bracket direction. It means it comes from the terminal and into the variable C. Okay. Sort of that's the idea how one should see this syntax. Okay. Next, let's say I have the outs. So it's the opposite one. Yes, right. The first thing we all write the hello world line and end it with a line. Okay. Now this is the output as an outstream. Okay. You redirect a text to the outstream, and also after that you redirect an ENDL as an end line. Now the important distinction between this is I hope the input and output parts are uh, clear. If you take a look at the standard ENDL itself, okay, what this does is what this does is it does a standard flush. Okay, that's like there is a line. Let's say there is some text which has to be pushed into the output stream. Okay, standard flush. So those things are first stored in a buffer. Okay, what standard flush does is it clears that buffer, so it forces it to print to the output, like as into the terminal. Okay, ENDL is this standard flush plus a new line. Okay, so a new line is defined by a slash n. Okay, um, right. Okay, so it's basically a combination of these two. You can actually do the same thing with this. It will and also add a new line. And you might have seen that having standard ENDL also adds a new line, but standard ENDL does something extra on top of it, which is, oh yeah, why are you calling them stream? Think of it like, um, I mean, I don't know how accurate it is, but okay, from thinking point of view, you can think of it this way. It's like water stream, okay? But instead of water here, there are bits. So the bits themselves flow into so this is the bitwise operation, right? You might have seen them, the double arrow, the double angular brackets, right? So those are usually used to manipulate bits. The bits flow into the input C. Yeah. So here it is actually also, you can think of it like here it's overloaded operation, where this operator here means in context of streams that bits flow into the variable or whatever text we have. So depends on here that input could be strings as in characters or integers or doubles or so on. So the double angular brackets operator themselves are overloaded. Okay. They accept strings also. And let's say here C is integer. So let's say we input integers. Now, this whole text is also, just give me a second. Yeah. So this whole text is also a sort of like a collection of bits, right? So those bits are also pushed into this C out stream. Okay. Is this an idea? You can visualize however you like. So, but the essential idea is that, yeah, sorry. But the essential idea is that there are bits in two directions. So one is the input stream and another is the output stream. Okay. I hope this idea is more clear now. Um, whole thing combined as in, do you mean the whole line itself, line 9, line 10, and so on? Okay, okay. Kind of, yeah, you can. But one has to be careful. It is the same output stream. Okay, I have this output stream here. So let's say I take this to example. This is the output. Here is the input stream. Here there are two lines of output stream. Okay. From perspective of output or input, there is only one pathway. Okay. You can separate them out into different lines. That is absolutely okay. All right. But here the behavior, I mean, think of it this way. There is a input stream. I input my data to it. That's fine. There is output. Okay. And there is text hello world with /n as a new line, and I end my line. So this in output stream has this bits of data for it to push to output. Again, to that, we also push another hello world, but this time with a standard ENDL. Okay. Now the difference is there's no guarantee that this will get flushed, as in it'll first maybe stay into buffer and so on. And depending on, again, that depends on implementation and architecture. And then this line also gets added to the buffer. Once it hits the standard ENDL, it forces it to print that full line. Okay. Uh, Something like this will be, I understand if we ENDL will also be part of output stream. Yes, that's correct. Yes, it will be. So if it, since we're running us just a simple C++ program, which is of single process, single thread, and so on, when you actually run multi-threaded operations, programs, or multi process programs with MPI, there you actually see this difference a bit more clearly, as in your output or input stream. Okay, let's say the output stream has some certain text. Okay, now that is there in some buffer. If you actually force it to clear, so for a given thread or a given process, it will get cleared, but maybe not so for the other case. So because they these operations become asynchronous. Okay. Uh, Seeing this buffer clearing gives more context. Okay. Anyway, the point I'm trying to make is ENDL is essentially a standard flush, okay, with a new line. You can always end a new line, but this doesn't guarantee the buffer gets flushed, as in buffer gets cleared to the output. To do that, you can actually do a standard flush or standard ENDL, which also acts as adding a new line. Okay. All right. I hope that is clear. We can also add more text to the output stream. Yeah. Okay. And print A. Let's go with an ENDL. And further, we can also add B and C. All right. And let's have it times 0 because why not? All right. Um, okay, let's take another example. This time I'll have the IO string. Okay. Another thing I'll include is a header file called IO manip, which essentially is the IO manipulation header file. Okay. So whatever IO we are performing, as in with text, characters, and so on, we can actually manipulate them. Okay. So let's look at some examples. Okay. So let's define an integer I, which is, let's say, 17. Okay. A long L. Okay. Uh, this time I will take it from an example. So this is in hex. Okay. Uh, this is some number, but represented in hex. Okay. Here it is a decimal representation. Here it's 0x. So it's hex. And after that, these digits represent correspond to some number. Okay. We try to print them and see. Okay. So let's go ahead with that. Find a long. Okay. So this is like the highest unsigned, and I'll define as unsigned. Basically, like this is the largest or longest thing we can store in a system. Okay. Call that as I64. And this time I'll store this back. Okay. I'll define another float f equals to, let's say, 15.0 divided by 7. Next, I'll define double. Yeah, the same thing. 15.0 divided by 7. Yeah. Then a character C, okay, which has of x. Then I will just do this one. Then a const character with a pointer. Okay, this will be a string. Let's call it VKP. Some text. Let me put it as Aman. Sure. And, then an integer. Okay, these are pointers now. So pointer p. Plus and I. Okay. Now let's start printing stuff. Okay. So this is usual. We have I. So print that. I think I did not intend to show this up, maybe I'll do that. That will be input. It's taking a while. All right, my bad. It expects an input. So let's give it some integer, or maybe all right. So it prints the hello world and the other inputs also, as in the other variables also we wanted to print. Six A as 6, B being 7.1, and 2 is the value stored in C, which we gave it as input. Okay. All right. Behavior wise, slash n and endl will be looking the same because they'll add in new line, but internally they are different. So just be careful of that. Next, coming back to this file, we have I, so we can print those. Okay. The second thing we can do is standard layout and x. Okay. I, oh, sorry, xi. Okay. So this is in hex. So what we can do is, oh, right. So what we can then do is put standard hex. Okay. This comes from the IO manipulations with I and put an end to line. Okay. Let's print this and see. So the first one is 17, right? So this is 7. And the representation of the same decimal number 17 in hex. Okay, so this is in 17 is the decimal representation. What we are saying is we want to represent it in hex, and that's what it shows as 11. Well, sorry, it's a question. Yeah, that's what. So the standard hex is defined under IO manipulation, as IO manip. Yeah. There are a bunch of some other things we'll use. So they are defined inside. Oh yeah, no. I think the maybe it is defined inside IO stream, but I'm pretty sure it's not. There's some other functions I'm going to use. Those I'm pretty sure are defined as, under IO manip. Yeah. So we'll see them now. The next thing we want to do is have the oct representation, okay, of I. So we'll just put standard oct, okay, and then put I. Then standard here. Now the number 17 represented in hex is 11, okay. Then we can see the same thing now for with oct. So in oct it is 21. Okay, as in 2 1. Okay. Next, standard cout. I'll print L. Standard. Okay. Here L is defined to be some hex value. Okay. Now the nice thing is it prints in the decimal form. You give the hex, how do you put it? The hex representation, okay. The default behavior is to show you decimal representation. So it prints in the decimal representation. Okay. Similarly, we will print the I64. Okay. The 64-bit represent like 64-bit number. So okay. The I64. Let's put it as standard input. Okay. Let's print that. So it prints the yeah. So this is like, I guess, the largest unsigned integer you can actually represent in your system, integer wise. Okay, integer. I'm not saying number, the largest integer. So this is that number. Okay. I think this is the largest signed unsigned integer you can represent, 32-bit. This is the largest 64-bit one. This one I'm not entirely sure. I think this is double of 65,300. Yeah, maybe. It's the largest one. That's how the X values are chosen. Anyway, the point is, this is the second one is the largest unsigned integer. So hence I added two long. Probably one long will also do, but anyway, that's fine. Yeah, it's from integer wise, no. Yeah. Well, depends on the use case. It could be big enough for most of the cases. It depends. Yeah. But integers being in two's complement, um, I don't see it to be. Yeah, that's fine. So what I was saying is integers themselves that we can. So it's like, let's say we have a way to. So the way we represent numbers, we have certain limitations. So 32 bits or 64 bits. So 64 bits also have a ceiling for integers. So because we use two's complement representation, we come to floating point representation, you can represent much larger numbers. That is true. Yeah. That's the thing about counting atoms. So think of it this way. When we represent any number using the scientific notation, we use scientific notations, right? Uh, let's say 6.578, so on, into 10 to the power 200 or whatever, right? Sort of the same idea to represent floating point numbers. Okay. And even, yeah, that's correct. Now, think of it this way. When the numbers become too large, into 10 power 200, let's say, I might not care about the decimals after a certain point. Yes, let's take the Avogadro number, right? So it's 6.023 into 10 to the power 23. So that's also a pretty huge number, right? But I probably can represent it pretty accurately to certain decimal places, okay, in my computer. And I actually don't require a supercomputer also. I can represent in any computer because I'll be only storing the first few digits. So 6023, and I don't really care about the rest of the digits till 23. You see what I mean? So into 10 to the power 23 means it has 23 digits after the decimal, right? But it's possible that because the number is so large, I might not actually care about all the digits. Okay. So that's where we can actually get away with while having errors, by which I mean not so precise number for a certain value. So let's say the Avogadro number again. So there I might be just okay with few digits. Let's say the first three or the first six digits. And I can use a float to represent this. That should be fine. Okay. Depends on the use case, but most of most of the times when we deal with very large numbers, okay, we tend to use the scientific notation, and scientific notation is the mm, model on which the floating point representation has been built. Okay, you can read up more on it, but essential idea is that using scientific notation, as in there is the floating point representation essentially uses the exponential notation with the mantissa and the characteristic and all of that. Okay. For what? Oh, no, you don't actually. So if you think about it, here the float that we have and the D we have, the double and float, they're internally represented using the floating point number representation. You actually don't have to separately link any library or anything. It automatically does it. Here we are dealing with very small numbers, so you don't see it. But you can actually manipulate the float and the double to be represented in scientific. Maybe we can take an example for that. Let's see. So, oh, that's why sorry about that. Um, yeah, so this is what we saw. The next we want to use is standard precision. Okay, let me actually that's more like set precision. Yeah, that's fine. So let me put it as 16, as in 16 decimal places. Print F, the float guy, first, okay, and the line of it. Same with B. Now, let's see the output. So 15 divided by 7, obviously it's not exactly divisible. So we'll have um, infinite digits, okay, in the actual proper, like the exact decimal representation. But our computers have limitations to precisions, okay. Floats are less precise than doubles because float have 32 bits to represent the number. Doubles have 64 bits. So in scientific notation, it will look something like this, as in here there's only 2.0. So you can think of like 10 power 1 into 10 power 0 into 10 power 0. But if I have larger numbers, it will be 10 into 10 power whatever. Okay. But if you look carefully, F and D are similar to certain decimals. So like I think sixth decimal. So 3, 6, 7. Yeah. Till 6 decimals, they are same, but in 7 decimal, they are differing. So the reason for that is usually floats are um, accurate to 6th decimal. Okay. When I say that, I have to be careful. It's not exactly precision hierarchy, yes. It's not exactly 6 decimal for all the numbers. It will be you have to think of it in relative terms, as in only for numbers which are like single. So it's for numbers into 10 power 0. Okay. Little hard to explain. As in larger the number, as in think of it this way. If I have into 10 power 200 or 10 power 50 or something, that's a much larger number. And the more away it is from 1 or 0, okay, the error actually grows. Okay, so maybe I'll not go into more detail, but think of it this way. If my number is closer to 1 or 0, then that idea which I say is the decimal representation till 6 will be the number will be accurate. That holds. It doesn't hold for all floats. Okay. Similarly for double. Uh, yeah, you can't ignore that. So it's essentially like the larger the number you are trying to represent, the more error it will have. Yes. Doubles don't have 32 point. They are till 16. 16 decimals. Yeah. But important thing again, I'll reiterate. Numbers which are closer to 1, okay, as in the actual absolute value 1, they are so something like this. They will have more accurate digits till like 6 decimal and so on. And when you go like into 10 power 50 or 200 and so on, then you can't exactly trust 6 digits. It will be much less than that. Okay. Yeah. All right. You can then also print P. As and say output. Okay. See, it prints X. That's what we know. Let me put it like that. Sure, because that's the name. All right, that is what we expect. The next thing what we can then do is standard cout. Okay, take this example where we are casting the pointer to a void pointer. See, this will be S. Okay, that's what we are trying to print, and a void pointer cast on S. Okay, let's do this now. So what what I'm trying to say here is S was a const character. Okay, so when we try to input it to the string, first the output string, first it prints S colon and then space. That's what we have. Okay, and S itself is, since it's a character, it prints each character. Okay, till it ends. So hence it prints the whole thing. Okay, so far so good. But if I treat, so S was the pointer of character type. Okay, but now if I treat it as a void pointer, okay, it has some characters, yes, all these characters, but now it is without any data type, as in what it should interpret them as. It's just a bunch of bits now. So when you cast it as void pointer and then try to print it, not exact null data type, it still has data type. I just casted it as to nothing. So hence it printed this text, as in this is the hex representation of that bits. It's, so the characters among, okay, they themselves actually take up some space, some bits. Okay, some combination of ones and zeros. But when I cast it as void pointer, I'm just saying that I do not have any idea what those bits actually mean. As characters, they mean Aman, okay? But as void pointer, I have no idea. But there is still a certain amount of bits. That those bits in hex representation is basically this. Okay, right. I hope this is also clear. The next one we can just say is the P. Yeah. And then just add P in there. Okay. That's it. This is the address of I. Okay, that's what we are storing. And important thing here, I don't dereference it. I just print P. So here it prints the actual address of I. So that's also an hex representation. Okay. All right. I hope things are clear so far. Any questions? Is void pointer S is garbage value or memory location of S? So one has to be careful still. Mhm. Since I'm printing SI and I haven't dereferenced it. Yeah, okay, let's do this. Let's print both. Here I'll just print S. Okay. Actually, that's what we are doing. Hmm, So now here one has to be a little careful. Uh, Printing P for an integer was fine because it actually printed the address. But for S, it doesn't print. Here it did not print the address. It printed the actual characters. Um, so when I say void pointer, what does it actually print? Okay. Yes, we can then do one thing. Mm. So put it on. Why not? Address S. Whenever in doubt, just print stuff. So there we can just put the address of S. Okay. Or let's make it a pointer. Don't need to put it as address. Let's put it as S. Because S is the pointer, I'm putting the address inside this long address. Okay. Now let's print S. Yeah, that should be okay. Let's do that. So ampersand S will actually print the address of the pointer, not the address that the pointer is pointing to. We can print that, but yeah, why not? Since we have done that, why not? Okay. This one is not allowed. Um, yeah, that's a constant character pointer. So we can then just bypass it and store. Okay. So the address of S is this. Okay. That's where the actual pointer is stored. Okay. This is the location, and this location stores an address, which is this guy. Okay. And the void pointer is pointing the same thing. Yeah, that is the address that it is pointing to. And that's it. Yes. That I guess that makes it clear. Yes. Okay. So, okay. So I'll summarize what's happening here. C itself was a character. Fine. But S being a const character pointer with basically characters. So here it knew how to interpret that. It essentially pushed all the characters till it ended. Okay. And actually printed the letters and or the text among itself. Okay. That's fine. Here when we did the ampersand S, it printed the address of the pointer itself. So that's what here it is. Now the pointer is actually pointing to here. So S, right? It is actually pointing to an address, to a location. That location's address is inside S. Okay. So that's what we store inside address S. Okay. And this is that address. So here so basically this is the point from which the bits bit representation of Aman starts. Okay. Next, if I convert it to a void pointer, okay, and then print it, I'm printing the same address, yes. But now because it is no longer a character pointer, it doesn't know what to do with those bits. So it just prints the address, not the actual data the uh, pointer is pointing to. Okay. All right. Hope that is clear. Uh, Next example. Awesome. I'll take a complex class, define double, let's call it real and imaginary as I am. This will be private. Now I'll have public. I'll define a constructor. Okay. So the constructor takes two values, underscore re and underscore im. Okay. Then it sets the data variables as such. Im underscore im. And the body of it is empty. That's it. So that's the public um, constructor. Next, our friend class. Friend function. All this as this will look a little weird, but don't worry, it will make sense. Operator. Okay. So the double operator, then standard O stream again. Ampersand S. Sorry, calculator OS as an output string. It takes an output string as input, which is this guy, the double angle bracket operation. Const complex type, yes. Ampersand P. And the body. Body is the out. And yeah, so half of it, P dot RE. Okay. These are not public. Oh yeah, that's it. Okay, that's fine. It's friend, right? So that's it. Okay. That would be it. Okay. Yes. Return. Yes. Ask the question. Um. Yeah. Print and then return. Yeah. That's correct. I know I wrote something. I'll explain it a bit. So let's do the construction. The setup also. Let's call it 4.5, 7.8. Okay. And another complex number. Okay. So here I'm defining the complex numbers. Let's say 2.5, 3.7, so on. It could be anything. And then I'm going to do something like this. C1. And yeah, let's put this way. C2 and the yeah, so, and yeah, that's it. Oh, my bad. I think this should be what that right. Okay, awesome. So okay, I know I wrote some bunch of things, but I'll explain each of them. So I think this is clear. This is a class, complex class. Okay, it has intermember variables RE and IM. So it's the real part and imaginary part. Okay, so far so good. Then there is a constructor. We have seen this before, which takes underscore RE underscore IM and sets them to RE and IM. Okay, I guess this is also fine. Come to that friend function. Okay, now let's look at the actual main function. So the complex data type is the custom class that we created. So to create two objects, C1 and C2, two complex numbers, I pass 4.5, 7.8 and 2.5 and 3.7. So I have one complex number as this is the this part is the real part, imaginary part, and again this is the real part and imaginary part. Fine. So far again, this is also I guess clear. Now What I want to do is, by default, complex numbers as in this object. Okay, so this is this object as which is the data type C1, as in this is custom data type complex. Okay, if I try to pass it to standard cout as in the output stream, okay, this will throw an error. Okay, let's say I don't have this. And as you saw, this worked fine, right? Okay, oh, sorry, my bad. This also. If I do this, this will actually throw an error. It throws a lot of bunch of things, but throws a bunch of things. But essentially, the main error here is that it doesn't recognize this operand, as in it doesn't recognize the object that we're trying to pass, which is of custom complex data type. Okay, to cout. And sometimes to make our life easy, okay, we define certain functions and certain code like this, so that if I want to ever print the complex number, I can just pass the object to it. Now remember, here the object, once it was after it was created, I don't have access to the internal member variables so that I can do whatever I did in this line 10. Okay. Ideally, yes, I can write this every time. But what if for the complex number, I do not have access to the internal member variables? One can even say, why not just write getter and setter functions? But let's imagine not for just this complex number, but for some class, you don't have its uh, you do not have access to its numbers, but there is a way you. I mean, okay, think of this. It's not like just you, but you yourself want it this way. You do want to give the option to print the number in a very neat format. Okay, but without the excuse me. Yes, sir. Yeah. So without the user even knowing what the numbers are themselves, as in access to the individual numbers. So this is a neat way of uh, overloading. Okay, here actually we are overloading the operator uh, uh, double angular brackets towards the left. Okay, especially left shift. That we are overloading. Why? As in how? We're making it a friend. Okay. The actual standard cout is also a class. It has the operator defined. Okay. By making this a friend, this function definition sort of like acts on top of whatever definition standard cout was already defined with. Okay. For now, you can also think like whatever standard cout was this had definitions. It has actually a lot of definitions for the left shift operator. Okay. Like we have been printing it for text, for variables, so on. Like, but these are inbuilt data types for which it is already defined. What we are doing is adding another custom defined definition. Okay, this is the data type for the output. Okay, that is fine, whatever. But what I want you to focus on is the operator with the left shift. Okay, this is the actual operator which is defined inside the standard cout. What we are doing is extending that definition for our custom created class also. How does that look? It looks something like this. Where you make it a friend with some data type, and that data type is standard O stream as an output stream. That is the actual data type which this operator will be in to make it a reference, so that when we return it becomes a reference return. It takes output stream in as input. Basically, it essentially means that whatever stream that it is a part of. Okay, I understand here it looks a little weird. There is no brackets, as in how to put it, like this with taking brackets. First is the O stream, and then the next is the complex type object C1 and so on. It doesn't look that way, I understand, but uh, believe me, this is sort of the also a function which internally takes a lot of how to put it, which infers all these things. So the C itself is basically this one. So C1 is what we're passing. Okay. The output stream is basically the stream which is part of the what we are putting it here, as in standard C out and out. So basically this is a stream. So that is the OS. We make this a part of that output stream and return that output stream. I understand that it might look a bit confusing, but I'll explain it again. I hope that makes things clear. But the essential idea here, what we're trying to do is we are overloading the left shift operator. Yeah, I understand. I absolutely get you. But that is because there is a simple function that you have written. Okay. Now imagine something like this actually is done for the standard C out. Okay. They have to do something. So code like this, which look very complicated, is actually written in production for standard template libraries. Okay. The reason for that is so that we can write clean code like this. Every time there is a integer or double or float or so on, we don't have to worry about it. We can just pass with a string of integers or like string of characters with my integer. And I can make this line as long as possible. As if you see here, it's actually quite large and it will still work. I don't have to take every case under the sun. Okay, I can make my output stream as long as possible. So let's say I remove these semicolons and standard couts and imagine standard cout, and then hex starts, and then this line, and then this, and so on. It's not they have to prove. Well, think of it this way. They do it because they can. All right. Also, there is like I show, there is good reason for it to write it this way so that it makes our life much easier. That's what a lot of code is all about. Even if it looks uh, scary at first, but the idea is that scary code like this makes uh, users' life much easier. So whoever is actually writing this kind of code, that's the essence of it. Okay. So I'll just repeat. So what we're doing is we're making the left shift operator. Okay. So operator double left is basically referring to that operator, basically this operator. It takes the whatever stream it is part of. Okay. And returns it before modifying it, as in after modifying it. How does it modify? It takes the object of complex data type also. All right. It's const reference. All right. Important here because we don't want to change the object at all. We just accessing the members and pushing into the stream. So the stream, we push the brackets, the real part with a comma, the imaginary part, and then another bracket. All right. And after this is pushed into the stream, we return that stream. Yeah. So the O stream is actually the data type. Okay. So standard C out, you can think of it like a class or a function. Okay. Okay. To actually do the operations, but it has a data type. That is this thing. O stream is the output data type. Similarly, the input stream has its own data type. But the point I'm trying to make here is this whole data is part of this whole stream is part of our data type. As in, I was talking about input and output stream, right? We can say O stream will return a class. Kind of, yeah. You can think that way. Yes. This is also in some namespace, this is a data type. And that data type is again a custom returns class. They can hover around and show, yeah. This is the one. It is this lib namespace OStream, which is a basic OStream with character. And yeah, I can't explain why it was written this way, but here it is. Yes. So this itself is So the stream that I was talking about, the output stream, the input stream and all, they themselves are a data type. Yes. And that is this one, the standard O stream. Yeah. To access this stream, but we never assigned OS to C. Oh, yeah, we did not. Actually, we don't need to. OS is actually this whole thing. As in, for this operator, okay, because we're talking about this operator, as in the double angle. Let's first, it's first encountered here, right? So this operator, as in this function, and I'll call it as a function, will take two inputs. First is the stream, which is it's part of. So basically, that is the standard C out. We have nothing in the buffer yet. So you can think of it like there's nothing in this operating, in this OS variable. And then it encounters C1 also. So that is this C here. It pushes, again, standard C out is part of the whole, think of it like recursion actually. So there is a standard C out to which we pass this whole thing. Okay. So now that becomes part of that OS. So now OS, which we are returning, is actually this. Okay. And then when it encounters, now take example for this angular bracket. For this guy, the OS, okay. But here it's important. For this one, it encounters characters. So it will not actually call this definition of left shift operator. Yeah. The more you look at it piece by piece, it gets more clearer. Okay. So for this function, left shift operator, this friend class won't be called because here the input is characters, which is already defined in the standard C out class itself. We don't see it, but it's already defined. It looks something like this, okay, and has its definition and everything, but that gets called. The second time when this left shift operator gets called, it triggers this guy because on the right hand side is C2, which is an object of class complex, which is this guy. So OS gets input. Here OS is this whole thing, including C1, whatever it had passed already, returned, right? Including the colon and space. That is the OS object output stream data type. Okay. That OS gets passed here. Added on to it, we add the bracket, the real part, the colon, sorry, the comma, space, imaginary part. If I give any integer after colon, that will not trigger the friend function. Right? Yes, that's correct. It will trigger the operator left shift, which is already defined for that left shift operator inside C out, standard C out in the STL library. Yes. Yeah. Okay. It's so the reason to write OStream OS is think of it this way. This is actually going in a sort of a recursion, as in the OS gets updated each time this left shift operator gets called. It's written that way to work. And again, one can argue, what does this left shift operator here means? It will call all those definitions that is already defined, not the custom definition. So yeah, it looks like a khichdi where the left shift operator once gets called from here and inside whichever we called also gets called. Okay, so it's sort of a recursion, yes. But the point is, for each operation, there is a definition on whatever it takes from the right hand side and adds to that stream. So that adding to the stream sort of looks something like this. So whatever is there, we add to it, okay, some sort of text and return that stream. Okay, if I didn't have all this and just had this, it will just add that single character and return the stream. Sort of that's what happens here. Okay. All right. So that's what OStream is. And we wrote a friend function because we want it to be accessible, like this function should be accessible outside the class, as in, and Outside the class, yes. And also it should have access to the member variables. That's why I made it a friend. You can, so yeah, then it will just add this line. So when we previously printed, we saw it printed the actual number and then semicolon and so on. Okay. But let's say, yeah, let's say I remove this. Then it will just print that twice. That's all. Yeah, it just prints that twice. For the first one, it's C1, right? So C1 thing will get called, it will print this. Okay. I did not get. Oh yeah. Uh, can you guess what will happen? I can do it. So it will be okay. Uh, you're right. It will happen that way, but there will be a small slight thing that will happen. P.re and RIM are private variables. So it will throw an error, but let's say we make them public, then it's fine. What you're saying is correct. Also, the other thing is when you put them in brackets, it will not actually print the actual variable, it will print the character C.re. Yeah. But yeah, if you remove the the quotes, then C.re will replace the variable. Okay. Yeah. No, that's the thing, right? So here I'm passing the object itself. But if I try to write C.re, I'm trying to access the private member, which is not possible because RE is private. I can't write. I can't write this. So something like this. Okay. It will actually print the character as in text itself. Okay. C1.re. Uh, but this is not allowed because this is private member. Okay. So here it will be just characters with space, colon and then space. Here it is the actual variable. Okay. But that actual variable is double and this left shift operator is already knows about it. That's fine. But the variable is private, so I can't access this. If I make them public, then yes, I can print it this way. Okay. Is that clear? Yeah. Awesome. Awesome. Okay. I think I'm still audible. Okay. Or there was a slight drop in the connection. All right. Okay. So, all right. Now we will move on and look at some file IO. Since we're talking of input output, it's not just um, text or characters or variables that we just input to terminal. This also sometimes deal with files, which like they're not always dealt like interact with terminal, but to the storage. So let's say we have some calculations that we do and we try to write it to the storage. So that's the one way of dealing with files. The other is reading from files. Yeah, we will take a look some examples and yeah, I mean, there is a structure to it. There are certain syntax that people generally, generally people deal with, and if you follow them, it's pretty. I would say at least things become easier. So let's look at some of those. All right. So uh, IOStream is the usual C outs and C ins, right? FStream is what you need for working with file management, file IOs. Okay, so that's the file stream. All right. Okay, let's look at some examples. Usual, we have main and return 0 for now. All right, so let's define standard O stream. So this is the stream for output. Okay? I'll call this as my file. And this object will act as the files object in my C++ code. What this file object is, I'll open it, give it a name. I'll call it text.txt and end that line. So essentially it means I have an object, my file. It will open a file with the name test.txt. Okay. And it is an O stream, as in it accepts an output stream. So to work with this, what I'll do is I'll write my file. Okay. Now since it is already open, and then put hello world. Okay. And then slash n because why not? And then same my file. I can start putting some numbers. Let's say one. Um, so let's say this is have 2, 3, 4, 5, 6, 7, so on. All right. Um, and sorry, and then 100 plus why not? And another line, we'll call it as some text. Yes, why not? And then because you opened the file, you have to actually also close it. That's a good practice. Okay. So internally, what happens is there is a handle to each file that is created. Okay. So first, the that is handled by the operating system, and you have a process which is this code. All right. Now, when you open that file, you sort of want to say, I'm the only one who's accessing it. Any other process should not have access to this file because otherwise it will lead to errors and undefined behavior and so on. So in this my program, my file becomes the object, okay, of data type of the class standard row string. Okay, this is what we saw before, and this will help me deal with all the files IO and everything. Okay, so now the file will open it using the name text. So this what will do is it will create a actual file in the storage. Okay, in your storage, as in could be SSD, the hard disk or whatever, of the name test.txt. Okay, and then to that file we are pushing all this output and then closing it. That's it. It's a pretty simple, straightforward way of handling it. One can go more um, uh, complicated syntax for managing files, but this is sort of the uh, basic way it looks like. So as to understand why we open it and then close it and so on. Okay. All right. Some of these things we tax, but the point is the base is this, the foundation is this. Okay, then something happened. I'll make a mistake. Oh, my bad. It's not O stream, it's OM stream. Yeah, sorry. No, it's sorry about the typo. So O stream is the stream for just normal text and all. You have to use OF stream, as in F streams output, okay, for the output stream for files, okay. Hence the F stream. Yeah. All right. It ran, it created a text file, okay, injected all this code and then closed the file. So let's see. So if I, so here's the actual file. One other thing, if you do not give the full path or anything, if you just give the text file's name, it will create in the same directory. That's sort of the default behavior. Okay. So if you see the test.txt, that's the default behavior. So wherever you're running the code, that's where it chooses. That's all. Here it actually means this as dot slash this. Okay. So yeah. So then when we see the text file, so we see the outputs, the output 1 to 700 and test.txt. So all the things are here, right? And let's say I delete this file. Sorry. Then I run it again. It created the file again and the corresponding text that we had. Uh, it actually created it, yeah. Because test.txt did not exist. It created it. So important thing here, when you say open and give the file name, okay, maybe I'll have it here, okay, and then run it again. Yeah, because it did not exist, it created the file and pushed all the changes. Again, the natural question is, what happens when, if it already existed, will it do all this? I think it will, as in, it will open it fresh and overwrite all the, uh, how to put it, overwrite all the things with whatever you are giving and then close it again. Yeah. But I'm not entirely sure, but I'm pretty sure that is the behavior. Can check that. But yeah, if it doesn't exist, then it creates it. Yes, that's correct. I did not get. I should log the whole thing. No, that's the thing about directions. Um, so assuming the behavior is, if it already exists, it opens it and clears the whole thing, as in overwrites the data, then what we're seeing is correct, right? So it doesn't matter how many times you run it, you'll always see the same 10 lines. And that's what happens. I run it again, it's the same exact line, same exact text. It's not like it gets added to uh, yeah, that's what I'm saying. It won't, because the behavior is, when you open it and it already exists, it probably overwrites that file or it ignores it. I'm not entirely sure. I'm not entirely sure, but one of those behavior. There is a way to append. So what you're trying to say is, what you're getting at is trying to add text to the end of the file. Okay. Yeah. So that is what we call as append. And I think there is an example I have which does this. Let's see. Okay, I do not, but well, can move to the next example and see the another syntax. But yeah, the idea is that how then we track our change in code. Um, Change in code you can track by using the version control systems like Git. But yeah, I don't think you mean that. So file change, yes. That's when actually it gets tricky. So it really depends how you're opening and closing the file. Do you mean so there are I'm not showing the syntax here, but you can read up more on this. You can open files in different modes. You can open them in read mode, you can open them in write modes, and so on and so forth. Okay. Now it depends how you are adding the text. Is it a redirect of new code, new line? So let's say there is a file which already has lines and you're redirecting some output to it. What that will do is it will override that thing. So let's say there were 500 lines in initially, and storing it in text format, it should track all data, right? It depends. That's what I'm saying. So if you are redirecting, yes. So if you're redirecting, then it will overwrite. So let's say there were 500 lines already. You are redirecting just a single number, 5. It will replace the whole 500 lines with just the letter 5 or just the number 5. So that's the redirection. If you're appending it, again, that depends how you're writing the code. Okay. You're appending it. Yeah, you have to make changes to the code. There is provision for that in F streams. Yes. Then it will add them line by line, line by line. Yeah. There is a code that we can do now. It sort of does the same. Let's see. Okay. Along with F string, I'll also need string this time. So let's add string header file. Next, I'll make a standard. Okay. If string, the input file string. I'll call it my file again. This time I'll give it the name test.txt. Now, important thing to note, the input or output. Okay. What do you call this? And it's called input or output with respect to your program. Okay. So if you see here, I had an object my file. It's inside my program, and I'm inputting as in that is the file. Yes, from my code into that file. So it is the output. Okay. Again, with respect to from my program, I output to terminal. So that becomes input output. From my text to object, as in the object is the file, that becomes the output. Okay. Input again is from terminal to my code. So that was the we saw from terminal to my code. So that is the input. Okay. So the reference, you can always think of it as your code as the base, and anything going out is output. Anything coming inside is the input. Okay. So here, correspondingly, I'll have a my file object. Okay. This one is the input stream. So it will take input from outside the code, which is this text file, which I already created. All right. Then what I'll do is I'll make standard string called line, right? So this will read lines from my file, which is already created test.txt. Okay. And then I will do that. If my file is open, okay. If it's open, like if I am able to open it, all right, then it is true, and I'll run this code of line. All right, I'll run a while loop, which has a function called getLine. Okay, and to that I pass my file. Press the one, and also a line. So getLine will, what it will do is it will take that object my file, go line by line, store it in line itself, which is the standard string. Okay, so no problem there. And this while loop will just print the line itself. So we're going line by line and printing each line. That's it. That's all we're doing. Okay. And we can add a new line or standard indentation. Anything is fine, really. Um, because we're running things this way, so maybe I'll just add new line. Okay. Then the while loop. Okay, I'll format this so that I don't confuse you. So the while loop is ended. Okay, I do not have anything inside. So this is the end for while loop. And then I close uh, close my file. End the line. All right. And this was the end of the if part. The else part, actually don't need this. Just have one line. Standards layout. So this is a check. Mm, see out to my file. Yeah, no, the important thing is the my file is something from which we are reading. We cannot directly pass my file to see out. Okay, because it will be string of text. We want to go line by line. So that's hence the whole deal. Okay. So the else part is yeah, I'll put unable to open file. So the else is because if the file is able to open, then all this is fine. If it's not able to open, it's obviously unable to open. So that's the sort of error handling that we're doing now. Okay. Good. And this will be number 5. Yeah, it prints all the text that we had already input. So the text, the previous example, we created the text file. Okay, so test.txt, the test file we created using the OF stream. OF stream means this my file is the output, becomes the output from my code. So from my code, I'm putting all these lines inside the file. Okay, and then closing it. That's it. That's all. Now that creates this file. That's fine. In the second example, I'm creating an if string as an input string from a file which is test.txt. Okay. If this file did not exist, then we'll throw an error. So I can try that also. So this I deleted. Okay. So if I try to uh, run input file, then it throws in unable to open file because I created the object saying that look for a text file which is test.txt. Okay. And if you're able to open this, then do all this. But if you're not able to open this, then you're just unable to open the file. Because that's what it did. If I run it, the the file with file name input output code.cpp, it creates this file. Okay. Now we're going to use this file in the second example, the output 5 example, and run this. So this will take open the file test.txt. Okay. And then sorry, yeah. Okay. So it takes this file test.txt. Yeah. So and then we define a string, standard string called line, to which we input each of these lines. And sequentially is what we want to print. Essentially how it looks here. We don't want to print each of the characters in a single line. We want to have each printed in each line of the terminal. So that's the goal. So to do that, okay, so this is the output. So we open try to open the file. If it is able to open, great. I will run a while loop. The neat part about a while loop is it will run until it is false. Okay. When does that happen? So the getLine function goes through the object, my file, puts each line, okay, it encounters into a line. How does it know what is the end of line? By default, in every system, okay. So here this is a Mac. So Mac has a certain rule to say when a line ended. Okay, we can't see it here, but every file has its own rules when the file ends. It's different for Linux, it's different for Macs, it's different for Windows. Okay, So every system has its own way. All right. So when it hits those characters, it knows that it's a new line. So get line will know that, puts everything until that character into the line that we pass, which is the standard string, and then we're printing it. Okay, with a new line. So that's what happens here. Sorry, that's what happens here. New line, new line, new line. After the while loop ends, so that happens when get line cannot get any more line. So so it sort of knows when the file actually ends. Okay, there are characters at the end of the file to demarcate that. So when it hits that, the while loop goes false, exits the while loop, then we close that file. Okay, so this is inside the if block. If we cannot open that file, that's when the unable to open file is thrown. This, which is what we saw before. Sorry, this is what we saw before. Okay, okay. We run this, and yeah, that's it. Okay, I guess that is that. Uh, that more or less covers what I wanted to cover today, which is the input-output I/O part of C++, both from the perspective of terminals, just numbers and strings and so on, and from file. So using F streams, IO manip, IO streams, so on, you can manipulate text either to the terminal or from the terminal, and you can also write to the file or the um, get data from the file. Okay. Yeah. With that, I guess we can end this to discuss. Yeah, the exception handling, I guess we can take next class. Yeah. Okay. Yeah. Well, it's not too difficult. So I guess we can uh, see few things for that. Yeah, I mean, if we take the basic try and catch, the most um, basic form of exception handling, it's basically like you try um, what do you call section of code. If it throws a certain kind of error, then it catches it. There are different kinds there. Again, yeah, I don't think simpler fine. Yeah, exactly. But more advanced, I'm only. Yeah, I understand. Then that's the thing about the exception handling. There are a lot of cases. I can't cover it them all, but yeah, if you're fine with understanding the simple errors, then I think I mean that's definitely a first step. You're if you're able to understand the basic errors. Advanced errors, I would say still it's the same, man. You have to, yeah, yeah. Simple errors are clear, right? So, but the advanced ones, you just have to get used to them. The problem is there are lots and lots of them, and even I'm not familiar with all the errors. It's yeah, it's like, think of it like there are, if let's say there are 10 cases, you just have to understand each case separately. And depending on how many of those cases your code might encounter, you have to write your code accordingly. Yeah, I know, sounds like a bit of a pain, but yeah, it is what it is. That's how exception handling is. So there is a okay. I'll still say this. There is a good reason why there are so many cases, because we actually encounter so many cases of uh, like the advanced errors that you mentioned. Um, Best way, again, take each case. That's my advice. So take each case, write some code, try to understand how each case works. Once you master every case like not, I would say every case, but let's say certain number of certain examples that are encountered frequently. Once you get used to them, then you will be, yeah, you can find them online also. Yeah. Just search for exception handling. And I think there are in the lectures that is given, there are more examples actually. So try to practice them. So yeah, um, you just have to get familiar with each exception handling. Yeah. Yeah, yeah, yeah. You can get them online. Oh, lectures also. Okay, okay. Then go for online. Yeah. The best way to get these resources will be, my point of view would be the actual CPP reference or the uh, C++ uh, uh, the documentation. Nothing will beat that. Yeah. We'll find all kinds of. Oh yeah, of course. Think of supercomputers as just collection of small computers. But okay, supercomputer is not just one computer; it's a distributed system. So a lot of computers combine to work in tandem in a way, and then become a PC, a supercomputer. That's all. Then why? As in, I mean, we have PC. Okay, I still do not get. Oh, you're asking if we have supercomputers, why do we have PCs? As in, if you have a massive supercomputer, then why do we need PCs? Oh, that is a very good question. But think of it this way: if I have supercomputers, why do I need phones? Or okay, sorry, my bad. I wanted to phrase it this way: if I have PCs, why do I have phone itself then? Why do I have another personalized device? Let's say if I have phones, why do I have watches, smartwatches? Why do I have any other smart device? No, no, and that's actually the point. It's not about power. It's actually not about power. It's about convenience. So supercomputer, yes, you have a huge supercomputer, which has like lots of computers combined to make a giant computer. Yes. But think of it this way. If everybody is accessing that supercomputer, it gets busy. And it so happens that it cannot serve your purpose instantly. But if you have your own computer, Uh, not always, because when we say a supercomputer, we can call it a cluster. Yes, a better name would be a cluster. Yeah, a collection of PC, you can call it a cluster. But a supercomputer, when we say there is a certain level of hardware that we mean to be a supercomputer, as in they do not consist of the. It is similar, but think of it this way: the consumer level hardware that we have, those CPUs, those GPUs, they are not the consumer level. They are much more advanced server levels, and with much more error correction hardware and much more robustness for even the storage. Okay, so because of those things, the actual hardware for each individual component of the PC, okay, which may or not, I would say PC, each node of the supercomputer also is much more advanced than a normal PC. Now, here's the thing. So when we say servers, they themselves also are a cluster. Yes. But when we say supercomputers themselves, we mean a certain kind of hardware for a specific purpose. So supercomputers usually have very powerful GPUs and CPUs to do tasks. Servers themselves, okay, when we say they could be just mainframes. When I say mainframe, it could be just a computer which does certain tasks very fast. What is a task? It could be just, let's say, for example, credit card transactions. So those kind of transactions do not need a lot of compute power or a lot of, um, yeah, it's basically a lot of compute power or a lot of memory. But they might need something fast, very fast I/O. So there are specialized hardware made for this kind of work, and they are termed into as mainframes. So mainframes are also servers. Yes, there are servers which also like cloud services, right, by AWS and Microsoft. Those are also a huge collection of this cluster. let me call them as clusters for now. A huge cluster which you can access to run your programs and such. But still, they also don't term it as supercomputers because again, it's at that point it becomes a nomenclature. It's like, how do we define supercomputer? Yes, it's also a very powerful hardware, maybe very similar to what we call as they are servers. Yes, they are servers, but not always termed as supercomputers, is what I'm saying. They might have the A100s, B100, the H100s, and the B100s, GPUs of NVIDIA, and the okay, there's again a distinction. Those AWS and Azure servers, they do what something called a virtualization. They partition they give you instances. They partition the same node into different pieces and assign each piece to a different user. Okay, supercomputers generally don't do that. Hence, they are hence AWS and Azure are not termed as supercomputers. Supercomputers usually mean a large cluster of nodes. Okay, you submit a job, it will take certain number of nodes, and that's it. The job will run, and there will be thousands of users running jobs at the same time. I guess, I mean, as such, everything is hardware and PCs and computers, yes, but it's how you look at it and that purpose. The purpose is very important. Yeah. Okay. I hope that is clear. Hmm. What does it make? As in, so okay, should we clarify this? So when we say order of n square and order of n, here usually mean the problem size, right? So depending on your problem and depending on the algorithm, yeah, right. So depending on the algorithm that you employ, it depends. It might make O(n) square problem to O(n) time. When we say that, that's not entirely correct because um, okay, think of it this way. If I have a problem which scales as n square and I distribute the task, okay, there's something called domain decomposition for something like that. So say for example, and again, okay, it depends on, I will say it depends on the algorithm. It might make O(n) square divided by P, where P is the number of processors you have. The processors as in, I mean, number of nodes or number of computers you're employing. By distributing, it is possible it might make, yeah, it might make n square by P. It might make n square to n also, depending on the algorithm that you're employing. It's not always that um, you can just change the complexity of a problem just by making it parallel. Yes, it affects its complexity. I'm not denying that. But when you are saying O(n) square becomes O(n), you are uh, ignoring the fact that there is a component of parallelism there. As in, there is no so so supercomputers have processors, right? There's like huge number of processors. Let's say call them as P. I'm ignoring nodes, processors, everything combined to one as P. So what does my P come? You can actually take read about RAM model. So there are models how to there are very basic models how to distribute tasks and so on. Yeah, they do. But that's the thing. It depends on your P. I'll write it. So uh, this is what people start with in basic parallel programming courses. So RAM model is one model where it assumes that you have infinite resources. How much parallelism can you achieve in your program? So that's sort of the idea. And then you try to do some complexity analysis. You can read from that. Again, not going to cover in this course, but just to give an idea, you can look at it. Okay. And yeah, yeah. they do have huge parallelism, as in they have the opportunity to have huge parallelism. Okay. The important thing is, can your algorithm exploit that? Meaning, you have a algorithm. Okay, so this is a serial code. Can you design a parallel algorithm code which can take advantage of the massive parallelism that your supercomputer offers? That's actually the main crux of parallel programming. Okay, it's almost always, I would say, the algorithm that will decide how your code scales or how fast it becomes. Okay. Um, so far, because we can't scale compute so much, but we can add resources. So far, that's what the parallelism has happened. Um, yeah, I mean, we have designed algorithms around distribute computing more. And yes, if you make individual distributed computer much faster, then the whole thing will also run faster. But it was easier to make algorithms first, and then again, anyway, the hardware themselves can get better. So a lot of focus has been towards making the algorithms much more efficient and parallel and so on for a given task. Yeah. So like graph algorithms, parallel graph algorithms, parallel, let's say sparse matrix multiplications on distributed systems, so on and so forth. Yeah. There will be always be things to learn. Um, Again, that's the fun part, I would say. Uh, while you're actually learning, it's the phase that you learn the most. I mean, that's when you actually have the most fun. So I would say still enjoy it. Yeah. Parallel programming itself is a huge topic. So from programming perspective, yes, serial programming is what we learn. And there's features also. That's the modern C++ that this course is. Parallel programming itself is also a huge topic. Yeah. Um, Again, parallel programming, I would say the prerequisite will be learning programming itself first. Um, First, you can start with OpenMP, then maybe move to MPI. And again, CUDA or GPU programming. You can have MPI with CUDA or GPU programming. Those are also stacked. So I'm sure there should be NPTEL courses you can look at. NPTEL should have these courses. Can go ahead and look. Yeah. That is another level, as in this was scaled from one side to the other. The lower level side, CUDA has PTX, I guess. Might probably, yeah. So C or C++, you can think that way. CUDA also is written, actually in Fortran also it is written. But you're fine with just learn. If you know C++, that also should be fine. Yeah. CUDA doesn't always use low levels language. It is low level, but it's like C or C++. You can go assembly level also for CUDA. Um, yeah. So what I'm saying is, sorry, you can also go assembly level like you do in CPU codes for GPUs. Yeah. The assembly for CUDA is called PTX. Nice. Thank you. Um, yeah, I mean, it's fun to teach. So hence, as part of my teachership, I'm doing this. It's definitely fun to interact with students, and it's always nice if you have. Yeah, it is. That's actually the uh, part I always mention. Learning part is always the most fun, so try to enjoy that part, because once you learn it, you go to the next one. So because you're still chasing that same thing. Yeah. Depends. It depends. Okay, so maths, I would say, see, not always you need it, but see, it's like if you have graph questions, then if you consider that as a lot of maths, then yes, maybe. It depends on the problem or the field you're working with. If you're doing finance and stuff, then yeah, absolutely, you need a lot of maths. If you're doing scientific computing, oh yes, of course. But if you're just doing simple programming where you just have to implement some stuff, then probably not. No. Yeah. Oh yeah. Quantum. So okay. If you're going to research, absolutely yes. And quantum computing, especially, you require. Okay, I'll say this. You require a lot of linear algebra. Make um, like take courses on linear algebra, but I would say you probably need advanced courses also. Yeah, and a bit of quantum mechanics. Learn quantum mechanics to understand quantum computing. Yeah, sure. Learn. I mean, whichever resource is uh, more suitable to you, you feel you learn it, go for it. Yes. All right. It's good to interact and teach. So yeah, thank you for that. Yeah. Yeah, sure. Basically in algebra, just get familiar with it. The advanced stuff, I definitely recommend learning because um, quantum computing can get very sophisticated if you're going into research. Yes. You can also look into the numerical aspects of linear algebra. So that is another thing uh, which becomes important because it's not just linear algebra that we care about because computers happen. So the numerical aspects become important because then we have to worry about precision, errors, and so on. Yeah. Yeah, you can go ahead. Yeah, sure. Sounds like a good idea. Yeah. All the best. All right. All right. So I guess we can end now today's class. Yeah. Awesome. We'll see you next week. Yeah. All right. Happy coding, guys.